let's see what's going on here. Let's see one scenario where something like this could be really, really useful. Okay, so it says right here, Jane wants to sell her car. Jane has a Subaru Forester, but she doesn't know what the listing price should be. Listing price is not what you sell your car for, it's the price you list it at. And this idea of listing it correctly at the correct price can be really important for how quickly you want to sell it. If you price your car too high, then no one will buy it, obviously, because they can buy other ones that are cheaper. But it can also be bad if you price your car too low, because people will look at it and go, wow, that's a really good deal. What's wrong with that car? So she's trying to figure out the best possible listing price for her car. So here's what she does. She goes to various, it says Jane looks at 22 Foresters. Yours only has one R. Mine had two at first anyway. There's only one R in this name. 22 Foresters for sale on various sites. So she goes to AutoTrader and all these different sites, CarMax, whatever. She goes to all these different sites that actually have Subaru Foresters for sale. She finds 22 of them and she pulls this data for these cars. She looks at the age of the car because that's definitely a component for how you price things. Newer cars are more expensive, and the older they get, the cheaper they get, because cars depreciate a lot, okay? Depreciate means the price drops. So she looks at the age of the car in years compared to the listing price. And she takes all of that data, and of course she makes 22 ordered pairs out of it. She makes a scatter plot with that data. She calculates the equation for the trend line for the data and puts it all on this scatter plot that you see here. And actually in this scenario, Jane is me. That's code for me. I did this. I don't really have a car to sell, but I made up this person, Jane, and said she had a Subaru Forester. But I really did gather this data. And there's all kinds of, once you understand that constructing a scatter plot is just plotting ordered pairs, it's actually really helpful to go to different sites like Alcula.com, or if you just Google scatter plot creator, you can find free ones online. And all you have to do is type in your ordered pairs, and it will create a scatter plot for you. And then you can even select for it to give you a trend line, and it will pop in the line of best fit. And it's always best if you can do something like that with technology, because when we draw it by hand, we make little errors. But this is officially the trend line that best fits Jane's data. Okay, so each one of these little X's is one of the Subaru Foresters that she found online. So if we counted through these, there's 22. Some of them are really close together, so they look a little mushed. But there's 22 little X's on here for the 22 cars that Jane found online. Now, there's some things missing from this that would make this a much better scatter plot. So the first thing we're going to do is we're going to add that stuff. It says label the X and Y axis of the scatter plot and give the scatter plot a title. So let me get my pens here. So I'm ready to go. So she compared, it says up here, she compared the age of the car in years to the listing price, how much they were trying to sell it for. So these are cars for sale, so we don't know if they actually are going to sell for that, but this is what people are selling them for. So I see down here on the x-axis, I see 2, 4, 6, 8, 10. That looks to me like the age of the car. I'm going to put age of car, and then I'm going to specify that this is in years. Okay. Are there any other components that affect the price of a car? No, I'll be thinking of that as we look through. And then that would make this over here, we got 4,000, 6,000, 8,000, 10,000, 12,000. This over here, I'm gonna turn my page sideways. This would be the listing price. And this is in dollars. Okay, so the other thing it told me to put on here was an overall title for this scatter plot. And I think a good title, because this is specifically what she was looking at, would be Subaru Foresters. That's what this is. That's what this scatter plot is all about. So it seems like a good title. Okay, so we did that. Label the X and Y axis of the scatter plot, give the scatter plot a title. Now it's definitely, we can look at this and we can tell what it's all about. Oh, okay, this is the age of the car compared to what it's listed for, and it's all about this type of car. All right, so just to make sure we understand what we're looking at here, it says find one specific age and price of a car that Jane found online. That's just making sure you understand, well, this is the trend line here that's going to help us make some predictions and use this data. Each of these little X's is an actual car that Jane found online. So we have many options here. I could pick something really close to the trend line. I could pick something, so for example, this X right here, if I follow that down, it looks like it's halfway. So this looks like a 1-year-old car that was listed for about $20,000. Versus I could also go for maybe like this guy right here. This is a 12-year-old car listed for about $4,000. So you pick any one of those that you want to. You don't have to pick the same one as me. I'm gonna just do that one, okay? That one specific age, I'm gonna write it as an ordered pair, 12, 4,000. And what that tells me is that that is a 12-year-old car. It's a 12-year-old Forester specifically, listed for $4,000. That is one she specifically found on sale. It was a 12-year-old car, cost $4,000. Okay, now we could go through and we could find all of that data and we'd have a list of 22 cars. That's the actual data that she used. So just make sure you understand that each individual X is the data. This is just the line of best fit, the line that best fits that data. Okay, now this other part, because the nice thing about using an online tool or a calculator of some sort to help you find this, I used it to draw the scatter plot. I let it put in the trend line for me, and it actually gives you the equation as well, which is nice because I don't have nice grid lines to count the rise over the run. And sometimes doing that by hand is not very mathematically accurate. So I am going to give you the trend line that I got from using an online calculator. It's a very handy thing. You can try it out yourself. But the equation for this trend line is y equals negative, you ready for this? 1,480x plus 24,250. Now, it doesn't ask me to write this down, but I do want to talk about it because it's interesting to look at. What does this slope represent? You're going to do that some more on this paper to make sure we're not losing that, because that's one of the trickiest things. So we need more examples of that. This slope, remember, slope is always y per x. So the fact that it is negative, which makes sense because I see a negative slope here, I see a negative association between these variables because as age of the car goes up, price of the car goes down. So this negative 1,480 means based on this data here, what they're telling me is that a Subaru Forester loses $1,480 worth of value per year. That's just every year it gets older. Now this is obviously on average, and the fact that this does not pass through every dot and that this is pretty scattered means this is definitely just on average a prediction. That's not exactly what's going to happen to every car, because what I see with this trend line here is I see lots of dots above it. That means these cars, these particular Subaru Foresters here, they are selling for more than the average, okay? And why might that be? Well, other factors that impact the price of a car are things like mileage, how many miles are on the car. That's another really big factor for price. So maybe some of these cars are a little older than their cars at the same price, so they're selling for more, but maybe that's because they have a lower mileage or some other factor. Whereas these cars down here below the trend line, maybe they have higher miles. So even though like these three cars were all the exact same age, these two were able to sell for more for whatever reason than this one. So, but what this trend line tells me is that a Subaru Forester loses $1,480 worth of value per year. And what this y-intercept tells me is that on average, the cost of a new one is $24,000 approximately, okay? And that, I would imagine if for real life data, there would be a little curve on the end because any car depreciates a lot in that first year. Anyway, so very useful trend line. Here's the new step that we're taking today to help us actually solve problems. Jane found all of this because she had a question. She doesn't know how much she should list her car for. And using all of this data and creating this trend line allows her to answer that question. Here's what Jane definitely knows about her own car. Her car is 9 years old. She knows the age. In my scatter plot, age was on the x-axis. So what that tells me is I actually have an x value. And I'm going to use that x value along with my algebraic equation here to help me find a y value, which will be the answer to Jane's question, listing price. So all I have to do is take this x value and plug it into my trend line equation. Negative 1,480 times 9 plus 24,250. You can just grab a calculator, type it in. Here's mine. Okay, so I'm going to go negative 1,480 times 9 plus 24,250. And, okay, I got $10,930. That is why the title of these notes is called Problem Solving with Trend Lines. You set up your scatter plot, you calculate a line of best fit or a trend line, and then once you get an equation for it, you can actually use that equation to answer some questions, okay? So I want you guys to look at this next part and pause for just a minute and take a look at this, because most of it is like what we did last time. So you're gonna give it a try, but let me read this to you right down here. It says, let's try another. In 1960, so 60 years ago now, wow. About 45% of the US population smoked cigarettes. That's almost half. To be fair, they didn't quite realize how bad it was for your lungs. It took them a while to realize that. But about 45% of the US population smoked cigarettes. The percentage of the US population that smoked cigarettes over the years since 1990, that should definitely say since 1960. Change that on your file before I put that through. But since 1960 is shown in the scatter plot, okay? So, and I know that because look what it says right here, years since 1960. So often they'll do this when time is on the x-axis, because taking this data all the way back to literal time 0, 2020 years ago, wouldn't really make any sense. So they took this data back to 1960, and then they just started marking 10 years from there. So pay attention to that scale. So this means 1960. This 10 actually means 1970, then 1980, 1990, 2000. So this is years since 1960. And this is the percent of the US population that smokes. So I want you to pause the video for a moment, and I want you to try questions 5 through 7. That is based on things we did in the last video. So pay attention to the rise over run, pay attention to the scale, see if you can get the equation, and then interpret M and B for me. Pause the video and try it. All right, let's see if we agreed or came anywhere close. So I found on this graph what looked pretty close to corners to me. So I got a corner-ish there and a corner-ish there. And I saw that went down 20 over 30, paying attention to the scale. Both are going by tens. So the slope is negative 2/3. So, and as I followed this back, it looked like 45, which makes sense because they told me that starting point here. 1960 was year 0, they told me 45%. So my B value is 45. So here's my trend line equation. The slope means that the percent of smokers in the United States decreases by 0.2% each year. And that initial value, our year 0, remember, was 1960. So this is talking to me about year 0, but in this case, that's 1960. In 1960, 45% of the US population smoked cigarettes. So again, this is initial value where the data starts, and this is how it changes. Now, we're going to take that a step further now. We're actually going to use this algebra to help us answer some questions. Now, be careful because things get a little tricky when you redefine it as 0 meaning 1960, when the years become like that. So for example, right here, what percent of the US population would you expect to smoke by the year 2015? So by the time that year came around, think of it this way though, 2015, we're talking years since 1960. So first we have to figure out, according to our data and the algebra that we use, what's the X value we want here, because it's not 2015. That would give us a really wacky answer because that would be 2015 years past 1960. So the first thing I need to do is figure out how many years past 1960 I am with just a little subtraction. So 2015 minus 1960 tells me that I'm really looking at the value 55. Now, the other thing I have to pay attention to is the fact that this was a year and that was on the x-axis. So now I can take this value 55 and I can plug it into this equation. Now, before I do that, I'm going to look on my graph too, because sometimes you'll notice on the work that you're given, sometimes what you're looking for is visible there on the graph, and you can use the graph to estimate or verify whether or not your answer is correct. Sometimes though, your answer is not visible on the graph. Sometimes it goes beyond the graph, and that means we have to use the algebra. So sometimes the graph, you can use it, sometimes it's too far and you can't use it. So if I look at 55 here, I can kind of get a guess of about where my data should be, but the line didn't quite keep going. So I'm going to plug it into my equation right here, but I can see it's probably supposed to be less than 10 because that's where the trend line's going. So I'm going to go y equals negative 2/3 times 55 plus 45. You can either use the fraction button in your calculator, or you can just type in 55 times negative 2 divided by 3 times 2 divided by 3 for fraction there, and then plus 45. Don't forget the plus 45 part. And what I see is y equals 8.3 repeating. So I just used x to figure out y, which in this situation was percent of US population. So according to this trend line, by 2015, and it's something we should be able to look up, I guess, since 2015 has happened 5 years ago, about 8.3% of the US population smoked cigarettes. Okay, that's according to our trend line if this pattern continues. Look at number 9, because this is where things get a little bit trickier. What if they ask it this way? When would you expect the percent to reach 1%? They're giving me a percent now, a y value, and asking me to predict the year, which is an x value. I can absolutely use my equation for this. I just have to plug it in for the correct variable. So if this is a percent, I'm going to plug it in for y. Here I go. 1 equals negative 2/3 x plus 45. Now I can't just evaluate. I have to do inverse operations and work my way backwards to solve. So I'm going to do that. I'm going to start with minus 45 minus 45. Yes, that's going to give you a negative, but that's okay because you have a negative over here that's going to take care of it. So remember, the easiest way to get rid of a fraction is to multiply by the inverse. Basic solving equations review here. I'm going to multiply by negative 3/2 to cancel that. And then, of course, whatever I do to one side, I have to do to the other side. Again, though, you can go negative 44, just times by the top number, times by negative 3, and divide by 2. And I get 66. Wait, what was I finding? I was finding x. When would I expect the percent to reach 1? 66? Oh yeah, it's 66 years past 1960. That's what that 66 means. So I need to go 1960 plus 66, and the actual year that I'm looking at is the year 2026. If that trend continues, I can expect about 1% of the US population to smoke cigarettes by 2026. All right, there's a little bit more on this on the back, just to streamline the process and practice just the new part to us, or just the most important stuff. On the back, look at these examples. Okay, we're going to try one at a time. I'm going to pause the video. I'm going to let you guys try it, and then we'll go over it before you try the next one. So this time, instead of me giving you the scatter plot, I took the visual away altogether. So this one talks about something that I think we talked about before on a homework. I already can't remember. But it says a scatter plot. Oh yeah, we did. A scatter plot was created with the trend line y equals negative 0.04x plus 5.5, where x is a person's age in years and y is the diameter of that person's pupil measured in millimeters. We talked about this and how old people shouldn't drive. So you're going to do what you did before. You're going to pause the video in just a second. You're going to tell me the meaning of the slope in this context. What does that slope of negative 0.04 mean? What does the y-intercept 5.5 mean in this context? So remember, y per x, y at 0x. And then you're going to try this extra step. If I start giving you some information, can you use the trend line equation to answer those questions? So pause the video right now and then come back when you have it finished. Pause. Okay. How did we do? So I have negative 0.04 millimeters per year, and we talked about this before, that means that your pupil is shrinking over time. And then 5.5 millimeters at 0 years, that's the dilated size of a pupil at birth on average. So number 12, please notice what they say up here is really, really important. X is a person's age in years, and Y is the diameter of that person's pupil measured in millimeters. That's how I know how to do these Y per X and the Y at 0X. And that's also really important to help me know where I plug these values in. Predict the pupil diameter of a 60-year-old. That's age, that's X. So I plug it in and just evaluate, 3.1 millimeters. Predict the age of someone with a pupil diameter of 5.34. That's diameter, that's Y. When they give me X, I can just plug it in and evaluate. When they give me Y, I have to inverse operations and solve it. So when I did the inverse operations, minus 5.5 divided by negative 0.04, 4-year-old. All right, let's read the next one and try the next one. A scatter plot was created with the trend line. There it is. Y equals 1.14x plus 21.58, where Y is the length of an alligator in inches and X is the age of the alligator in months. Hey, they switched it around. Don't let that throw you. Y is the length in inches and X is the age in months. So give this one a try, interpret M and B, and then try to answer some questions using the equation. Pause it and give it a try. Voila. How'd you do? How'd I do? I'm sure you guys will let me know if I made a mistake. Not that that ever happens. But this means the alligator was growing at a rate of 1.14 inches per month. Make sure you did Y per X and not accidentally X per Y. And this 21.58 is the inches at birth, how big the alligator was at birth. Now, look at this one. If the alligator's 42 inches long, inches, that's Y. So this right away, I had to plug in 42 for Y and use my inverse operations and solve for X. I got about 18 months old. Hopefully you got around there. And then this predicts the length of an alligator that is 12 months old. This one gave me X, so I could plug it in and evaluate. How are we doing? Doing okay? Last one. Let's try one more. And then you should be ready for a little bit more practice and an assessment on this stuff. So a scatter plot was created with the trend line Y equals 0.0009x plus 2.9. What is this about? Let's see. X is the year since 1975. Oh, tricky. And Y is the amount of lean in meters from the vertical of the Leaning Tower of Pisa. It keeps leaning, keeps leaning. All right, so you're gonna try one more. You're gonna pause the video one more time, interpret M and B for me, and then use the equation to answer some questions, and let's see if we got it. Pause one more time. And that's it. Now be careful with the years since 1975 thing. So for example, here, they gave me the meters, which is Y. So I plugged it in and used my inverse operations. But then when I solved it and got this like 62.3 years, then I added that to 1975 because this is years past 1975. So that would be the year 2037. So make sure you didn't forget that step. Now this one I had to start by adjusting that. Next year would be 2021. I'm talking years since 1975. So in order for the algebra to work and make sense here, I've got to subtract that. And that means X is 46. It's 46 years past 1975. So plug in 46 and it's about a lean of 3.0053 meters.